Let's dive into a mystery that connects a rock that fell from the sky with the super strong steel we use every day. It's a story about a beautiful, but really confusing, pattern that made scientists completely rethink the rules for how atoms build our world.
So where does this all begin? Well, not in some high-tech modern lab. Nope. Our story starts back in the 19th century with a simple observation of a meteorite and the incredible patterns that were hiding inside it. So there's this guy in Vienna, Alois von Widmanstätten, and he's studying a slice of an iron meteorite. And as he's looking, he notices these absolutely stunning geometric patterns of intersecting plates. What he was seeing was the result of the meteorite cooling down incredibly slowly over millions and millions of years out in the cold of space.
And get this is where it gets really fascinating. Decades later, scientists who study metals, metallurgists, they've found the exact same kind of plate-like structure in steel. The only difference? The scale. In the meteorites, these things were huge. You could see them with the naked eye. But in steel, they were microscopic. This just blew people's minds and raised a huge question. What in the world is the atomic process that could create the very same pattern in two completely different environments?
Okay, so to really get to the bottom of this, we've got to do a quick crash course in how atoms can actually reorganize themselves inside a solid material. It turns out there are pretty much two main ways they can do it. And the difference between them, well, that's the key to this whole puzzle.
Now check out this slide, because this analogy is just brilliant. On the left, we have what's called a military transformation. Think of it like this. All the atoms move together in a disciplined, coordinated way. Every atom keeps its original neighbors, just like soldiers marching in formation onto a bus. It's really fast, but it physically distorts the material, creating a whole lot of internal stress. Then on the right, you've got the civilian transformation. Here, the atoms just kind of move around individually, breaking old bonds, forming new ones, like civilians getting on a bus and finding a seat next to their friends. This process avoids all that stress, but it's way, way slower, because the atoms need to be able to actually move around.
So here's the twist. This specific structure we're talking about, this Widmanstätten ferrite, it doesn't quite fit into either box. It actually follows a third, kind of hybrid path, a paramilitary transformation. What does that mean? Well, in steel, the big iron atoms, they snap into their new positions in that disciplined military way. But the tiny little carbon atoms, they just get out of the way. They move around individually, civilian style. This is our first huge clue.
And this right here is where the puzzle really kicks into high gear. Because when scientists started looking at the evidence, it was pointing in two totally opposite directions. It was a massive contradiction, and it just didn't make sense.
On the one hand, you can literally see the physical result of the transformation. I mean, if you polish the surface of the steel nice and smooth before these plates form, you can actually watch them physically push and shear the surface. It's undeniable proof of that coordinated military-style movement that causes a huge change in shape.
Now, a shape change like that, it doesn't come free. It costs a tremendous amount of energy to handle all that strain. Think of it like an energy tax the atoms have to pay. And it's a big one. We're talking over 400 joules per mole, which in the world of atoms is a massive, massive energy bill.
And this is the paradox. This is the heart of the mystery. We know for a fact these plates form at pretty high temperatures, where there's only a tiny bit of energy driving the change, nowhere near enough to pay that 400 joule energy bill. So how is this possible? How does nature build a structure that it seemingly can't afford to make?
Well, the answer, as it turns out, is incredibly clever. It's just elegant. Nature found a loophole. The solution wasn't about changing how one plate grows, it was about changing how the plates grow together with each other.
Okay, just picture a single one of these plates trying to grow all by itself. Its military-style shear is like taking a single tent pole and just shoving it up under a flat canvas. You get this huge, awkward bulge, right? The strain on the surrounding material is just immense. The energy cost is way too high.
But what if you use two tent poles and you push them up back to back? That's the genius of this solution. The plates don't grow alone. As you see here, they form and grow in pairs. Each plate in the pair is oriented just a little bit differently, so their individual pushes and pulls on the material mostly cancel each other out. What you end up with is a nice, stable, tent-like structure where the net strain is dramatically reduced. They found a way to work together to pay the energy bill.
So this self-accommodation is the secret sauce. It's why these plates can form even with a tiny energy budget. But, there's always a trade-off. Finding two perfectly matched starting points to form one of these pairs, that's a pretty rare event at the atomic scale. and that means the final structure grows very coarse, with really large plates, which can sometimes be a bad thing that makes the steel less tough.
So, we've cracked the energy puzzle. Awesome. But that just leads to another question. What controls how fast these plates actually grow? Well, the answer lies with those tiny mobile carbon atoms.
As a plate grows, its speed all comes down to a really delicate balance. On the one hand, a sharper, pointier tip can cut through the material faster. But on the other hand, creating that really sharp, curved edge actually costs more energy. It's kind of like surface tension in water. A sharp curve is just harder to maintain than a flat one. A flatter tip is cheaper energy-wise, but it grows a lot slower.
So what happens? The growing plate has to find the sweet spot. It can't be too sharp because that's too expensive. It can't be too blunt because that's too slow. It naturally settles on this perfect Goldilocks shape at its tip that gives it the fastest possible growth rate for the energy it has available. It's a perfect balance of speed and cost. All right, let's bring it all home. What is this puzzling structure? Well, at its heart, it's a displacive military-style transformation for the iron atoms. But we call it paramilitary because those little carbon atoms are doing their own civilian thing, just getting out of the way. The big energy mystery is solved by that clever trick of growing in self-accommodating pairs. And its speed? That's all dictated by that Goldilocks balance between how fast carbon can move and the energy cost of the plate's own shape.
It's really just a beautiful, complex dance of atoms, all happening on a scale we can't even see. And it really makes you wonder, doesn't it? What other incredible, elegant solutions like this are hiding in plain sight in the materials we rely on every single day?